Hello guys, welcome to my YouTube channel dedicated to data structures and algorithms. In this first video of my channel, we are going to dive into one of the most important skills that you will need as a programmer, the power of observations. So being able to observe patterns and trends is crucial when it comes to designing and implementing efficient algorithms. And it's a skill that can be owned through practice and dedication. In this first video, we will explore that how to use the power of observation to identify problems, optimize algorithms, and ultimately become a better programmer. So let's get started. A prerequisite for this DSA Booster course is that you know the basics of any programming language, be it Java, Python, C Sharp, JavaScript, anything. So let's come to the topic, and we will understand this power of observations through a sample problem. And the problem is to count the factors of a given number n. So factor of a number n is any number that divides n completely. So this is a very simple problem. Let's see that what we are expected to return in this problem. For example, when my n is 24, then its all factors are 1, 2, 3, 4, 6, 8, 12 and 24, a total of 8 factors, so we return 8 as the count. If n is 10, we have 4 factors, 1, 2, 5 and 10, and we return 4. So the first solution, the brute force solution that comes to anyone's mind is that we just need to go from 1 to n, and we need to keep track of all the factors of n, and we simply return it. So let's have a look at the pseudocode of this brute force solution. As you can see, we initialize the count to 0, we go from 1 to n, and we check if I is a factor. We check it through the modulo operator, we increment the count if it is a factor, and in the end we return count. Let us now try to think that what is the time taken by this algorithm. So basically it's an order of an algorithm, but in this video let's skip using this term because I will be explaining this term in the next video on time complexity. So for now, let's try to think in terms of the number of iterations that this code is doing. So the I goes from 1 to n, which means a total of n iterations is being done by this algorithm. So let's now try to map this iterations to seconds, because ultimately we want to see that how much time is it gonna take in seconds. So over here we take an assumption that 10 raised to 8 iterations, 10 raised to power 8 iterations take up 1 second. This is obviously the processing power, and in most of the online judges like LeetCode, HackerRank or Topcoder, this is the time limit that you get because this is the processing power that they have, and it is 10 raised to 8 iterations, 10 raised to power 8 iterations take up 1 second. So let's see that what is the effect on time taken by this algorithm on increasing the input size n. So initially my n is 10 raised to power 8. It will do n iterations, so it's 10 raised to power 8 iterations, and the time taken is 1 second because 10 raised to power 8 iterations take up 1 second. We increment n a little bit. Let's make it 10 raised to power 10. The iterations are again 10 raised to power 10 and time taken is 100 seconds, because if 10 raised to power 8 iterations take up 1 second, then 10 raised to power 10 iterations will take 1 upon 10 raised to power 8 into 10 raised to power 10, which is 100 seconds. Now let's increment n a bit more. Let's increment it to 10 raised to power 18. The iterations are 10 raised to power 18 because it is n iterations, and the time taken is 10 raised to power 10 seconds. And this is 317 years. Now this is insane because we are not going to be alive to know the answer to this input size n. So here comes the power of observations, and we need to optimize this algorithm so that we don't have to wait for 317 years to know the answer to this problem. So let's see that what observations can we make to optimize this algorithm. So the first observation is that the factors come in pair. But how do you reach to this observation? So if you basically try to look at the brute force solution and what we are doing in the brute force solution and where is the point that we can optimize, you can see that we are checking for all numbers that whether the number is a factor of n or not. and we are running a loop. The loop variable is I. So whenever you check for any number I, that whether it is a factor or not of n, and if it comes out to be a factor of n, then there is another number j also, with which I would be multiplied to make it equal to n. So if I is a factor of n, then there is another number j also, which is a factor of n. So at the point we are only incrementing our count by 1 because we see that I is a factor of n. But now we can increment our count by 2 because we know that there is another number j also, which will be multiplied with I to make it equal to n. Hence j is also a factor of n. And this j, if you solve this equation, then this j comes out to be n by I. So the other number is n by I. So the factors come in pairs of the form I and n by I. So now let's try to find that what will be terminating point where we need to stop counting the factors. So over here I have drawn a table. So this is I, this is n by I, and let's make one more column which represents the count of factors. Let's initialize it to 0. So when we check for 1, then it comes out to be a factor of n because n modulo I is equal to 0, and the other factor is 24. So now we increment the count by 2 instead of incrementing it by 1. Again, when we go to 2, we know that the other factor is 12. So we need to increment the count by 2. It's 4. Similarly for 3, the other factor is 8, which comes in pair with 3, and we increment it by 2. It's 6. Similarly for 4, we increment it by 2 and it becomes 8. But now, as you can see, the factors have begun to repeat. 4 and 6, we have considered it, and now it's 6 and 4, the same pair of factors. So this is the point that we need to stop. If you look more carefully, then till now, the factors were of the form in pairs of the form smaller number and then the greater number. This is because we are going from 1 to n. So when you are at 1, the other number in this pair is 24 in this factor pair. For 2, the other number in this factor pair is 12, which is greater than 2 because we are starting from the smaller number, so the other number will obviously be larger. For 3 it's 8, for 4 it's 6. But when you go to 6 and you try to find that what is the other number, which is n by I, so 24 by 6, it comes out to be 4. So this 4 is smaller than 6, and we have already considered this pair before, 4, 6. So there is no point considering the same pair again. So we stop at this point. So we stop at the point when we get factors of this form, the greater number first and then the smaller number. We need to stop over here. So this is the point when my first number, because this pair was of the form I, n by I, so when my first number is greater than the second number, at this point I need to stop. Which means that we need to keep iterating till the point my I is less than equals to n by I, because we will be stopping at this point, and it means that we need to continue only and only till this condition is true in our loop. I is less than equals to n by I. But there's an edge case also, guys, which we can also clearly see that what if my I is equals to n by I. In this point, we cannot increment the count by 2 because we were incrementing the count by 2 because the factors were coming in pair and the factors were distinct. But if my I is equal to n by I, it's the same factor being counted twice. So this leads us to the second observation, which is the case of perfect squares. So let's see it through an example. I have taken n as 100, and when I reach this point, when my I equals to n by I, then over here 10 and 10, I cannot increment by count by 2. I need to increment my count only and only by 1 and not by 2, because it is the same factor being repeated twice. So you need to take care of this edge case of perfect squares. So now we are done with the observations. We have reduced the number of iterations. So now we only need to go till the point my I is less than equals to n by I. We only need to go till this point, and we will initialize our I to 1 and we will take it till this point. Also, Now we will increment our count by 2 instead of incrementing it by 1, as we saw that the factors come in pair. Also, we need to take care of the case when my I is equals to n by I. In this case, I will increment my count only and only by 1 and not by 2. So this is the second observation and this is the first observation that we made. So now let's look at the pseudocode for this better solution. So this is the pseudocode, guys, and over here as you can see, I initialize my count to 0, I start my I from 1, and this thing is the same thing which we discovered. I is less than equals to n by I. We need to go till this point, so we can write it as I into I is less than equals to n. If you solve this equation, it comes out to be this. So, and we increment I, and now if I is a factor of n, which means n modulo I is equal to 0, then we need to increment our count by 2 or by 1 depending upon the condition whether it is a perfect square or not. So if it is a perfect square, then we increment the count by 1 only. So for perfect square, we had seen that if my I equals to n by I, which means that I into I, we can write it as I into I is equal to n. The same thing is written in the if condition. We increment our count by 1, else we increment our count by 2, and in the end we return count. So the total iterations that we are doing over here, let's try to find it out. So we are going till the point I into I double equals to n. After this we stop, which means I square is equal to n, which means I is equal to root n. So we are doing a total of root n iterations. So now let's see that what is the time taken for the earlier input size 10 raised to power 18. So the number of iterations now would be root n. So 10 raised to power 18, if we do the square root, it's 10 raised to power 9, and the time taken is now 10 seconds. Because if 10 raised to power 8 iterations take up 1 second, which is the processing power, then 10 raised to power 9 iterations will take up 1 upon 10 raised to power 8 into 10 raised to power 9, which is 10 seconds. So this is the optimization, and we have been able to reduce 317 years to merely 10 seconds. Now this is amazing, and this is the power of observations. So guys, this is it for this video, and I hope you found this introduction to the power of observations in data structures and algorithms to be insightful and helpful. In the next video, we will be diving into one of the most important concepts in computer science, that is time complexity of algorithms. So be sure to tune in for the next video, and don't forget to like and subscribe to stay up to date with all the content coming up on this channel. Thanks for watching. Bye.